Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I am dealing with spectroscopy for chemistry. I will start a new topic of spectroscopy, that is IR spectra, and this is first lecture for IR spectra. Okay, and here in this lecture I will explain you introduction of IR spectra, that is vibrations of molecule. Okay, so see, when we start any uh, lecture, first of all, we should know what is the basic concept of this lecture, okay, or what is the basic concept of IR spectra. So it starts with, in fact, chemical bonds. In this chapter, we are dealing with mainly chemical bonds in organic compound, because we have to find out IR spectra of organic compounds, okay. And that is why which type of chemical bonds present in organic compound, that we'll have to see. And we know that chemical bonds present in organic compounds are covalent bonds. There are mainly two types of covalent bonds, sigma bond and pi bond. Well, in any case, if we see the basic thing, then normally during covalent bond, sharing of electron pair takes place. During covalent bond. That is very important. Let us take examples to understand this. So we will take example of hydrogen, which is having one electron and which will combine with chlorine, and we will have HCl, a single covalent bond, which will be sigma bond, and here sharing of electron pair takes place, one from each. So hydrogen and chlorine has to provide one electron for sharing, okay. And next thing about this in detail, which is given by valence bond theory. So according to valence bond theory, we have to explain the bond between hydrogen and chlorine. So let us take this way. Hydrogen is having nucleus and one electron in first orbit, okay. Chlorine is having nucleus, first orbit, second orbit, and third orbit. We are interested in the last orbit only, where there is one electron, okay. Now these two atoms, one is hydrogen, another is chlorine. These two hydrogen and chlorine atoms approach each other for formation of bond. And in this case, there will be two forces acting on them. One is attraction, another is repulsion. So to understand this, first of all, we have to label this nuclei and electrons. So let us call nucleus of hydrogen P1, electron E1, nucleus of chlorine P2, and electron E2. So obviously repulsion will be between P1 and P2. Both nuclei will repel each other, that is sure. Okay. Where is attraction? Attraction is between P1 and E2. That means nucleus of hydrogen attract electron of chlorine. Simultaneously, nucleus of chlorine will attract electron of hydrogen. Okay. Now, when this hydrogen and chlorine is going to combine to form a covalent bond, the very first condition is that they should have unpaired electron with opposite spin. This is the first condition. Okay, that means E1 and E2 should be having opposite spin rotation. Okay, in that case, E1 and E2 attract or repel. Well, normally we assume that electron being equal charges repel, but no. If they have opposite spin, there will be attraction between E1 and E2. The reason is magnetic field produced by nuclear spin, electron spin. So these two opposite spin of electrons become opposite magnetic field, north and south, like that. And therefore there will be magnetic attraction between E1 and E2. So here we can see that attraction is comparatively greater than repulsion. So when attraction is greater than repulsion, then these two atoms approach each other and they come closer and closer. Okay. So if they are supposed to form a covalent bond, then the first requirement is overlapping of atomic orbitals. According to VB theory, valence bond theory, overlapping of atomic orbital is must. Without this, they cannot form a single bond. Okay, so we thought that these two, hydrogen and chlorine, because of attraction, come closer and these atomic orbitals overlap. Remember, these two atoms do not have control on each other when they are approaching each other for attraction. And that is why they will not stop where the attraction is equal to repulsion, but they will cross this limit. And let us see how these two cross the limit and produce a new type of overlapping. So first of all, let us see this one, that they cross the limit and overlap with each other like this. This is hydrogen. This is a nucleus of hydrogen and overlapping of chlorine like this. And here we have a nucleus of chlorine. So hydrogen and chlorine will be at this distance. So the distance between two nuclei, P1 and P2, let us call it R1. But at this distance, R1, they are much closer and therefore repulsion is greater than attraction between hydrogen and chlorine. Okay, so they cross limit and they are coming more closer. R1 is a very small distance between nuclei of hydrogen and chlorine where there is more repulsion than attraction. Okay, obviously if repulsion is more, they will go away from each other and they may reach to this distance where hydrogen and chlorine will overlap, but very less overlapping takes place, and they will reach to this distance where now we can say R2 distance where attraction is greater than repulsion. Okay, so here H and Cl chlorine are at far distance where attraction is greater than repulsion. Okay, so hydrogen and chlorine will be here now where there is a very small overlapping. But in this case, because of more attraction, they will come more closer and they will reach to R1 distance. Their repulsion is greater than attraction. So again, they will move to R2 distance. From R1 to R2 and R2 to R1. They keep on moving and this is known as vibrations. So atoms continuously vibrate. They will never stationary. Okay. So we assume that there should be a distance between hydrogen and chlorine, which we consider a neutral distance where attraction and repulsion should be equal. like this. So this is the distance. We consider this as R0, where hydrogen and chlorine are not so far, not so close also, so that attraction is equal to repulsion. But remember, these two atoms will never achieve this distance. Then how to find out R0? Well, we know R1, we know R2, that from X-ray analysis we can find out these two distances. So R0 would be R1 plus R2 upon 2. That is average distance. Okay, so it is called average bond length, where attraction is equal to repulsion. But remember, these two atoms will never achieve this distance, and therefore they keep on vibrating between R1 and R2 distances. Okay, that is called basic vibrations of molecule. Okay, they will never become stationary at R0 distance. They keep on moving from R1 to R2, R2 to R1. Okay, but they will never achieve R0 distance and become stationary. And that is why every covalent bond is not stationary. Okay, every covalent bond or every molecule in covalent bond having covalent bond is not stationary molecule. That means atoms within molecule keep on vibrating. Thus, atoms within molecule keep on vibrating. Okay, they keep on vibrating, and that is called basic vibrational level. Every molecule has different basic vibrational level, different basic energy, and it has different energy. So it is also called basic energy level. And we assume that molecule is stable, but within molecule atoms are not stable. As hydrogen and chlorine at R0, and let us consider this as average distance. R0 is known as average bond length. And you know how to find out average bond length. Okay. So if HCl is having different electronegativity of hydrogen is 2.1 and chlorine is 3.0, that means these two are having different electronegativity, and therefore the electrons of bonding will be towards chlorine, partly towards chlorine, and therefore hydrogen carry partly positive charge, chlorine carry partly negative charge. So it is a bond in which you will find partial covalent bond and partial ionic bond. Such bond is known as polar bond. It is not completely covalent, not completely ionic. It is known as polar bond, and therefore each polar bond has definite dipole moment mu. Mu is equal to E into R0, where E is a charge and R0 is the average bond length, and the unit is dBi. Okay, it is always for polar molecule, and remember mu cannot be 0 for polar molecule. Okay, so this is basic about IR spectra. That's it in this lecture. Thank you.